Welcome back, everyone. Hope you had a nice break, got some food, bit of exercise, hopefully a little bit of sunshine from wherever you are in the world. And welcome back to the second half of DevOps. And for our first talk, back here in the DevOps track, we have a talk by Petertc Chu called Things Might Go Wrong in a Data-Intensive Application. I'm intrigued to find out what possible things could go wrong. As we all know, there's an endless possibility. So with that, let's take it away, Peter.
Hello everyone, I'm here to talk about my DevOps experience about building a data-intensive application. So what is data-intensive application? Well, I think there is no formal definition, and I will adapt the idea from Designing Data-Intensive Application written by Martin Krugman in my talk. In this book, we call an application data-intensive if data is its primary challenge. The quantity of data, the complexity of data, or the speed at which it is changing. The non-CPU circles are bottleneck. From this idea, we can say almost all successful online business are based on data-intensive system. To design a data-intensive application, we need to consider not only functional requirements, but non-functional requirements, such as reliability and scalability. And we already have many success stories from Google, Amazon, and Facebook. It tends to let us think, we can just follow their architecture to build a reliable and scalable system. We can just introduce things like Stability or Kubernetes, and then, whoa, now we have system can keep reliable and scalable. Well, I won't say totally wrong. And I thought we should notice the bias here. Those stories are just in effect a snapshot of their current situation, not the cause. They maybe have different requirements compared to your place, and they don't tell you how to get there, how many mistakes they made in the past. And that's why we are here today. I am a software engineer from Taiwan, as well as a Pythonista like all you guys. I am a PSF contributing member and organizing PyCon in Taiwan. By the way, PyCon Taiwan will be held virtually this year, so welcome everyone to join us online from October 2nd to 3rd. You can get more information on our website if you're interested. Back on track, the main point is I've been working on data-intensive systems for many years, and I'm glad to share my experience with you today. Let me introduce the case we study today. It's a data managed platform. We host user data for various usage patterns and workloads, such as online streaming, IoT data aggregation, file distribution, things like that. Currently, it hosts several petabytes and transfers several terabytes a day. In case you don't have a feeling about these numbers, I Google some vectors with you. For example, size of GitHub Arctic code vault is 21 terabytes, and Java's data lake has 34 petabytes of data currently. And here is a fun fact. If we put all our disks on the ground, we can cover whole football field. And of course, this case cannot be compared to those giants, but I think it's more practical case for most people, since not everyone has the opportunity to build a Facebook or Google from scratch. This is what it looks like. I think it's a common architecture of a large-scale distributed system. At the top of the diagram, we can have reverse proxy and stateless application servers, which are responsible for receiving and serving user requests. On the bottom of the diagram, you can see we have various kinds of data technologies to store structured and unstructured data. We use sharding and partitioning to distribute loading to different nodes. Also, we adopt distribute file systems to store unstructured data. There are some other subsystems for job processing and data analysis. This is just a very rough diagram, I know, to just allow you have an idea. I won't go through it deeply since today we focus on mistakes we made, not how we succeed. In the following time, I will tell you 4 of many incidents I made in the past years. The first 2 are about scalability. The others are about reliability. Finally, we will review what we can learn from these incidents. So here we go, incident 1. One day, we had a new customer. They upload their data generated by thousands of devices to our platform 24/7, 365. We never saw this usage pattern before, and as you might expect it, we cannot handle it. I trace the issue and figure out the problem is in database. For efficiency, we use optimistic locking in our system. Optimistic locking means the system doesn't lock the data explicitly before we manipulate it. We use it because we ensure our workloads will not cause contention very often, but will run. A straightforward solution is to switch to pessimistic locking, which ensures only one thread can manipulate data at each time. But it actually causes many problems. Performance of other usage patterns downgrade since their workload are suffering from unnecessary locking operations. In the end, I decided a hybrid and adaptive approach to address the issue. Hybrid here means we introduce both optimistic and pessimistic locking in our system. Operations that may encounter contention, such as writing, will use pessimistic locking. The others keep use optimistic locking as before. On the other hand, adaptive means by default, operations just need to obtain a lock from application servers before processing. This is not a real pessimistic lock, since operations may still complete while doing updates in database. We call this local lock. While conflict is detected, where conflict is actually occur, the system will ensure the real pessimistic locking automatically. We call this global lock. And it will be more clear in this diagram. You can see local locks can be obtained from each application server, and global lock are obtained from databases. In this approach, we can satisfy all users and their usage patterns. This is how this case was solved, but what can we learn from it? Well, in my opinion, the root cause is we didn't predict a usage pattern like that. In all our test scenarios, optimistic locking just works fine until we encounter this scenario. This is a classical scalability challenge we might see while building a data-intensive application. We will go back to review our lesson learned later. Let's go to the next one first. So what happened this time? We have an optional data manager feature for users. Basically, it scans and removes expired files for user. It's just a prototype at that time, since almost no one used it for many years. At that time, it was actually implemented as a simple cron job. We didn't care about it until one day, a user found it and made 1,000,000 times more requests to this poor cron job. Now I knew this feature is necessary for our customers, so I will implement it in a robust and production-ready way. What I need is a job processing system. We found one from GitHub called Rescue, which uses Redis as a job queue and can process tasks in a distributed way. So what can we learn from this incident? Again, of course, this is a scalability challenge. The difference is the pattern is exactly what we expected this time. What we unexpected is the law. Next one is about reliability. We know security is also an important non-functional requirement of a data-intensive application. So we, more specifically my boss, decided to outsource our data protection module to a professional security service provider. The project runs smoothly until we deploy it. We start to receive complaints that their data is corrupted. That's very weird, because not all but just part of data is corrupted. What's going on here? I found the problem is the encryption process. The encryption algorithm is block-based, so we have to add padding before we encrypt it. Let me explain how padding works in case if you don't have related background. We assume the block size is 16 bytes in the following examples. First example, if the input size is 12 bytes, we need to append 4 fours to the data. After that, it becomes 16 bytes and satisfy the rule that the size of data must be multiples of block size. In other case, the data size is 16 bytes this time. What should we do? We still have to add in padding. This time, we add 16 sixteenths at the end of the data. It's already satisfied the rule. Why should we do that, you may ask? Because in the decryption process, we need to remove padding to recover original data. The algorithm uses the last byte to identify how many bytes of padding need to be removed. That's why we need to padding in this example, even though its original data size is already multiples of block size. So now we can back to the original problem. Data corruption occurs because the implementation of our encryption algorithm only consider the case 1 in our example, but not case 2. That's why some users complain their data is corrupted, the others not. Fix this bug is trivial, but we have to fix corrupted data in the system as well. This is where reliability issue differs from others. We are not only fix the code, but the data. Correct data is also trivial. We just filter corrupted data by metadata stored in database. Then we can correct corresponding data. Use this table as an example. Data corresponding to first and second row is not affected by the bug since it's not processed by an incorrect algorithm. The third row is also not affected, since its size is not multiples of block size, even though it's indeed processed by an defective algorithm. The fourth row is affected, but it's already fixed. We distinguish it by the version number. We need this column since we will correct this recurse in a distributed way. We will discuss it later. The last row is the lonely one, need to be fixed here, since it was processed by an incorrect algorithm, and the size is multiples of block size. It's not yet marked as a fixed record. Indeed, in general, we will say this is just a silly bug, and most times we can fix it with our pen. But for a large-scale system like us, it's not funny. The bug affects millions of files in our system. You can imagine it's a very, very straightforward emergency situation. We evaluate the situation, and we found that if we use basic Python script to fix it, we need hundreds of days to correct all affected data. No way, we can do that. No user will wait us to do that. So we decided to use a distributed way to get the things done. We use a job processing system called Gearman this time. We don't use Redis as a job queue since we want tasks can be kept in a persistent storage, not in memory this time. So the root cause is obvious. We had an unreliable provider. But why can we figure out the problem before we deploy it? Right? Remember, the data is affected by this bug only if its size is multiples of block size. And as the block size is 128 bytes, then we only have a 0.7% chance to find a bug by testing. So the lesson here is, besides increasing test coverage, we also need to consider how to tolerate software faults and human errors in the production, because there is no way to prove a code is corrected or not. And okay, last one. This is the last incident I will share today. We didn't just screw out the user data. Guess what? We lost data too. We lost it not because we don't care about reliability. We did. We stole multiple replicas in multiple data centers while receiving user data. That's what we do in our system design. So, but why this happened? The background is the system not only considers reliability, but also load balancing. We will consider both system usage and failure domains while choosing a location to store data. This implies that newly added nodes will have a higher chance to receive data, since they have more resources available compared to old nodes in general. And here is another fact is, new machines have a higher chance of damage. This is called bathtub curve. Combine these two things cause the incidents happen. Data written to newly added node and newly added node broken, that's why. This is another classical reliability trend caused by a hardware fault. On small scale, these things already happen. Many people never backlog their computer because they don't think this will happen on their on their computer. But in a large-scale system, data loss happen regularly. And the bad news is it's almost impossible to solve it completely. I can tell you how many works we did for this. We did a week-long run test. We keep writing and reading data in the system while we're doing lab test. We even go through the data center and plug out the Ethernet cable directly to see what's happening. We also analyze system reliability by some theoretical methods such as Markov chain. If you're interested, you can go to and see SLA, that means service level agreement of your cloud provider. I think there is no one guarantee 100% reliability. In the end, what can we learn from these stories? 3 takeaways. Before we start, I have to remind you that it's a lot of be subjective. You can agree or not, and also welcome to discuss it later. First, no sleep bullet, classical. We've seen successful stories from Google or Facebook. When I was a junior engineer, I may think, their stories are so amazing. We should keep following their tech stacks to build a reliable and scalable system. However, after the my journey, I know that there are many things behind the scene. But why? Why can't we just follow some blueprints to build a reliable and scalable system, like building a bridge or a tower? In my opinion, first, it's hard to enumerate all possible reliability causes, just like what I showed you previously. Even though we do many preparations, data are still corrupted or lost. Second, pattern and law keep changing while your business expands. You cannot get a final version of a spec that tells you how many kinds of workload we will have and how many requests per second are needed. As a software engineer, I think that's a very interesting and very unique challenge we need to deal with. Second, you may think, that's bullshit. Those incidents will not happen if you have some fancy techniques. Yeah, that's fair. I believe a talented engineer can prevent some or many incidents we had. But she can use LS entry in most right scenarios. She can, use event sourcing to scale a system out. Or she can introduce puzzles to get strong consistency or adapt consistency hash ring and irrational coding in their system. But there's one more thing I have mentioned yet. Apart from reliability and scalability, maintainability is also a key maker. In his book, Martin Kerpman stated that reliability, scalability, and maintainability are the 3 most important factors while designing a data-intensive application. Although the incidents I mentioned are primarily about scalability and reliability, maintainability also plays an important role behind the scenes. Generally speaking, a data-intensive application is also a large-scale system, right? It's essential to have a talented team to support and involve it. No one can do it by herself. Here is an example I heard. Kafka, we know, is a multi-queue our string in processing system, right? Usually, it's just a component in a data-intensive application. But you know what? In LinkedIn, they had hundreds of engineers to maintain it. Why do I mention this here? Because I know you guys are those who are willing to challenge yourself. That's a good thing. That's a good thing. But I recommend you to think twice before you introduce some advanced techniques in your stack. Consider your team have ability to maintain it or not. Now you may think, you talk a lot, but does that mean we doesn't have anything to do to build a reliable and scalable system? I have no answers here, but I think the most important thing we learn from this instance is people. People behind the systems and machines are matter. People are the most important part of a service. Actually, we, engineers, provide service to our customers, not those machines. Machines are just our interface and tools. We need talent engineers to notice scale problems and fix them before the bad things happen. We need engineers to tolerate and troubleshooting reliability problems. Also, we need SRE engineers to build an infra that has least opportunity to cause human errors. The infra can also help developers to figure out problems in a more productive way. Finally, we need supervisors and project managers to understand it's important to have a good development culture. This is my zen of data-intensive system design. If you have experience I shared today, you may have similar feelings about these things. If not, I learned these things the hard way, and I hope this talk will save you from repeating the same mistakes. Thank you.
Well, thanks, Peter. That was excellent. Lots that I agree with there, which is just tremendous. I particularly like the emphasis on maintainability that you mentioned there towards the end of the talk. I think that's something that we often overlook, and the fact that it's all being looked after and managed by humans, and largely, as all of us here in the DevOps track are well aware, the humans are where a lot of the challenge comes from. So thank you so much for that talk. Now, Peter is actually here in the chat. So if you have questions about anything that was in the talk there, do drop it into the chat, and hopefully Peter will be able to answer those questions. Thank you so much. That was tremendous. Now, between now and the next talk, we have another break. So drop in some questions, have a chat amongst yourselves. Otherwise, yes, grab a quick drink, stretch your legs, and we'll be back at about 3 p.m. for the next talk. See you soon.